Hello and welcome to Agents of Tech, the show where we dive into the minds of the greatest innovators tackling the world's most transformative science and technology challenges. I'm Matria Godfrey in Washington, D.C., and today we are exploring the dawn of the quantum age and the global spotlight on quantum science as we approach the United Nations International Year of Quantum Science and Technology in 2025. Today we're looking at how quantum breakthroughs are reshaping our understanding of the universe and the future of technology with Professor Erica Carlson, Professor of Physics and Astronomy at Purdue University. The United Nations proclaimed 2025 as the International Year of Quantum Science and Technology. This year-long worldwide initiative aims to increase public awareness of the importance of quantum science and its applications. It recognizes 100 years since the initial development of quantum mechanics. I am so pleased to have joining us today Layla Rizvi, the Director of Research and Strategy here at Webb's Edge. Layla is also our in-house expert on all things quantum mechanics and joins us now. Thanks so much for your time today, Layla.
Thanks for having me, Audra. It's great to be here.
Can you give not only myself, but maybe for the folks listening who are not that well versed on quantum mechanics, a little bit of a history as well as a discussion on some of the outstanding questions?
I think the best way to describe quantum mechanics, because it's thrown around a lot in various different contexts, is that it's essentially the study of the very small. What it allows us to do is explain behaviors of energy and matter at a very small microscopic scale, which classical physics essentially isn't able to explain. And we're able to kind of leverage these behaviors in quantum systems to achieve things we wouldn't otherwise be able to do. The other thing about quantum mechanics, unlike classical physics, is that it rather than predicting exact outcomes, it predicts probabilities, which is something which tends to throw people off because, you know, we don't go around the world trying to predict the probability of everything we do. And historically, quantum mechanics was first developed in kind of the early 20th century, and it was difficult for a lot of people, and particularly physicists, to initially accept because it was counterintuitive to their experience, to everyone else's experience of the world, but also it didn't necessarily reconcile with classical physics theories. Quantum mechanics isn't actually that old, and so that a lot of questions still remain. This includes, why does observing something change its state at the kind of microscopic level, at the small level? How to reconcile quantum mechanics with Einstein's theory of gravity and concepts like spooky connections between particles, which is known as entanglement, where one atomic particle or quantum particle impacts the state of another.
The future of quantum science and technology will shape the 21st century, addressing global challenges like climate change, energy, food security, even clean water, and all of those are key priorities in the United Nations 2030 Sustainable Development Goals. Well, this international year is offering a chance for everyone, especially curious minds like ours, to discover how quantum science influences the world around us, from technology and policy to the economy, art, and even culture. So to help us explore these exciting advancements and understand the importance of the upcoming International Year of Quantum Science and Technology, we are thrilled now to welcome Professor Erica Carlson, a renowned quantum physicist from Purdue University. Thank you so much for your time today.
Thanks for having me.
All right, so can you start things off for us today by sharing a little bit about your journey in quantum physics and what really initially sparked your interest in the field?
Well, not surprisingly, I had some inspiring teachers. So my first inspiring teacher was my dad. He's an engineer, and it was just a joy to follow my dad around in our basement and explore the world with him. He would just show me things and show me how things work, and it was just a joy to learn about the world around me. I had a very influential set of teachers, especially as science teachers, and my first introduction into quantum physics that I remember was in ninth grade. Can you believe it? So in ninth grade biology, I was asking too many questions in class about how things worked. And I was particularly curious about water and how this was playing into how these molecules worked. And my excellent biology teacher, she was not flummoxed by the fact that I got to the end of her knowledge. And she said, you know what, Erica, there are some interesting things here, and I'm going to bring you an article tomorrow. I read an article recently about water and the quantum mechanics of it, and I'm going to bring you that article. So she brought me that. I think it was maybe just 2 pages. It was short. And it talked about the quantum mechanics of water and explained that the molecules have these electron clouds around them, that the electrons aren't little points and that's all they are. They're also clouds. And I was completely fascinated, completely hooked about how these strange shapes that the electrons take and the waveform could be affecting even our biology.
I think the cross-disciplinary nature of quantum mechanics as well. I mean, there's quantum coherence in photosynthesis as well, but that always blows my mind because I'm also from kind of a biology background. But Professor Carlson, I want to move more into your own research, which spans superconductors, liquid crystals, strongly correlated materials. Could you tell us a little bit more about how that relates to the broader world of quantum science?
A lot of my research has focused on superconductivity. Superconductivity is an example of something that is a patently quantum effect. You can't sort of pretend that the electrons and the atomic cores inside of a material are little balls and still get superconductivity. The key to superconductivity is that electrons pair up and that little pair becomes a new type of particle. We call it a composite boson. And that new type of particle can do something totally different, which is that they can all those little electron pairs can go into the same state, the lowest energy state, which is part of the quantum mechanical magic, if you will, of how superconductors can carry current without losing any energy at all. And you mentioned also liquid crystals. In the high temperature superconductors that are cuprate based, it seems that those electrons, before they do that pairing trick, they actually go into what's called a liquid crystal state. They look kind of stripy, so imagine a bunch of stripes where the electrons can flow like liquid along one direction, but they're crystalline, they're rigid in the other direction, and that's the liquid crystal sense. So we think that liquid crystal nature forms kind of a backbone on which the superconductivity arises.
It's really fascinating, and I want to talk a little bit about your educational initiatives and kind of how you've married quantum mechanics with present-day technologies, including your use of podcasts, Wikipedia pages, and the YouTube channel, The Quantum Age, all aiming to make quantum mechanics more accessible to those of us outside the field of physics. One, thank you for that. And two, what inspired this approach, and how do you think these tools have been helpful to kind of demystify the complex concepts for the general audience?
Well, I tell you what, I grew up in the South in Alabama, and my granddaddy was a Southern Baptist preacher. So I heard a lot of good teaching from him. And one of the things that was so fun about watching how he interacted with audiences is he'd always start off with a joke. He'd always connect with people, and he always met people where they were and drew them into what he was talking about. And so that has really inspired how I communicate, my communication style. I always want to meet people where they are. I know what it feels like to hear somebody and not know what they're talking about and feel lost, and I hate it. And I sort of imagine most people probably hate it. So I prefer to meet people where they are, talk about something that I know you already know, and bring you from that thing that you already know into the more esoteric world of the quantum. And another really inspiring communicator for me is Richard Feynman. So Richard Feynman, the Nobel Prize-winning physicist, when I'm trying to figure out how to explain something in quantum mechanics, I go back to the Feynman lectures every time, because the Feynman lectures on physics, especially on quantum mechanics, he's really good at breaking it down into plain English that we can all understand. And at the same time, and this is extremely important to me, Feynman is always right. So as a scientist, my job is to find truth and communicate truth. I really strive very hard to make sure that what I say is both accessible and at the same time correct. And that's an art. It takes practice.
Yeah, definitely. And I think that balance of accessibility and complexity is just, and being right is so important. And I agree with you in that Feynman does that amazingly, that, you don't actually have to dumb things down in order for them to be accessible, or not tell the full story in order for them to be accessible. So I think that's amazing. I now want to go from, I guess, education and accessibility, Professor Carlson, more onto kind of, again, research in the field. A question I love to ask scientists is, what they think is perhaps underappreciated in their field. So in this case, in the field of quantum mechanics, and something that you conceptually find particularly fascinating, or you wish more people in the field knew, or more people generally knew. I like asking this question because I feel like some of the biggest breakthroughs in science are often in areas which not everyone is working on, or the spotlight isn't necessarily on.
Well, one of the things that I find most fascinating about the quantum world is this duality between particles and waves. And you've all heard of it. If you've delved into quantum mechanics at all, you probably heard that phrase, particle wave duality. But the wave shapes themselves are so beautiful. And oftentimes what people miss in that sort of esoteric phrase, particle wave duality, is the wave nature itself being something you have so much experience with. So, for example, here's my slinky. I never leave home without my trusty slinky. And, the slinky does really cool things, right? It can make little wave shapes, and it can make another wave shape. There are distinct wave shapes that you can get on a slinky. And that same physics is exactly why we have the periodic table from quantum mechanics. So what's going on there is if you can kind of bend your brain a bit and go from the slinky having just one degree of freedom or one spatial coordinate to thinking about how electrons take standing wave shapes around the nucleus of an atom, that's amazing to me. So, you've probably heard of the 1s state. Maybe if you took a chemistry class, the 1s state that the electron takes is actually, it's a spherical wave. It just looks like a little fuzzy ball. But there are these other shapes that the electron waves can take that have nodes in them. You may have heard of a p wave state that has sort of the two lobes, and there's an actual node in the middle. It's all extensions of the wave nature of electrons. The electron waves take these standing wave shapes where they're wiggling back and forth, but it's a very regular motion. And it leads to these beautiful wave shapes that can get very complicated in the high energy states, but in the low energy states, they look like stuff you're familiar with, like a ball.
Fascinating. All right, I want to turn now to the UN's 2025 International Year of Quantum Science and Technology. So it's fast approaching. This is so interesting that the UN has declared 2025 as the International Year of Quantum Science and Technology. But I wanted to ask you in particular, what does this global recognition mean, do you think, for your field? And then also for engaging folks like me, maybe a wider audience, people who aren't necessarily as well-versed in the world of quantum science?
Well, I'm obviously very excited that they've declared this International Year of Quantum. Certainly, I'm a big fan of quantum mechanics, and I love communicating it to people because of its sheer beauty. It's a birthday of quantum mechanics. It's the 100-year anniversary. So this might sound like it's kind of old science, but at the same time, some technological advances have happened that have really allowed us to finally leverage quantum mechanics and start using it for our benefit. For example, we're going to see a lot of advances in quantum materials. A quantum material is something where we've taken the quantum properties that all materials have. Okay, all materials are using quantum mechanics, but those quantum properties don't always come to the forefront where we can use them and control them in technology. So a prime example of a really early one that humans harnessed is actually magnets. So how many people have a magnet hanging on their refrigerator, and actually you're using magnets in the speakers that you're listening to this right now? So magnets actually can only exist if you have quantum mechanics. We have an actual theorem in classical mechanics that says that permanent magnets are impossible. So it's a patently quantum effect. And so I would argue it's the first patently quantum material that we humans harnessed. Now we're at a completely new stage though. We don't discover new materials by digging them up out of the ground as we did with the lodestone, but we actually create new materials atom by atom sometimes. Sometimes it's by mixing them up and baking them and getting crystals to grow, but sometimes we just fabricate them like Lego pieces. And so we're continually creating new quantum materials, again, trying to pull those quantum properties to the forefront where we can control them and use them.
Do you feel like you've got 1 year to really try to capitalize on, the International Year of Quantum Science and to try to engage the public as much as possible?
Well, I'm certainly looking forward to that. I mean, we'll be releasing content on one of my YouTube channels, is The Quantum Age, and we do several different types of things there. So I have a few videos that are little quantum nuggets, things where you can, just maybe over a cup of coffee, that sort of time period, learn one quantum concept from scratch, from nothing. I have some interviews with quantum scientists so you can learn what's going on, what are we so excited about. And I also delve into more quantum materials like I talked about. So that'll be, for example, an opportunity to learn more about it. And I do think it's important for us to be engaging people. It's such an exciting field, right? Like I said, we're moving into new areas now where we can begin to apply these quantum technologies and bring them into our lives as new technologies. It's hard to predict. It's very hard to predict exactly where it's going to go and exactly what we're going to get. I like to compare it to, when we develop a new quantum material, it's a little bit like developing a new pigment, that you might hand to an artist. What could Picasso do if you handed him a new color, right? So in the same way, it's like the basic sciences people like myself working on developing and understanding new quantum materials. We create these new pigments, and then the engineers are like the artists who take those new pigments and paint a great new future with the new technologies.
That's a really fascinating way to look at it, because you're opening up truly like a whole new world of possibilities just by creating one new material.
So, as you were saying, the International Year of Quantum is a great year for us to focus on communicating those things and communicating those exciting discoveries. Like I said, there's so much beauty going on in the field that I hope people will delve in. It's not a subject that's 100 years old and that's it. There are some open questions. I think we're going to learn a lot of new things about the way the world fundamentally works. And so it's a great opportunity for the public at large to kind of join into our discovery process, learn about what's so exciting about the field, learn some basic quantum stuff, but also learn the new discoveries that we're finding.
I wanted to go back to your analogy, Professor Carlson, of, pigments being provided to artists, and inventors are like artists, and I think that's a fabulous analogy. Going kind of back to your work, which delves into fundamental quantum behaviors, including electron interactions, how do you think this work will potentially shape technological advances to come? I know you said that we can't predict it necessarily, but in your mind, what could we see?
So, for example, one of the things that I work on is superconductors. And, they're a patently quantum effect. We still are having conferences and arguing about exactly how the best superconductors work. If we can understand that and harness that, one of the technologies you'll see is that we could, say, convert the power lines from regular metals that leak energy all the time into superconductors that don't lose any energy as they transport that current. I mean, can you imagine if your water pipes or your gas line leaked as it was bringing this utility to you? We don't accept it in other utilities, but with the power lines, we have to accept that as they're carrying power to us, they're losing energy the whole time. So that's a great way that if we can understand it well enough to develop new materials that will work and have their superconductivity happen at ambient temperatures and ambient pressures, things that'll work outside in all seasons, then we could go a long way towards solving the energy crisis if we didn't leak all that energy along the way. Some of the other great things that are coming online are quantum computing. So that takes a lot of different quantum materials to pull that thing off. There are a lot of different material platforms that people are exploring and using to pull together these things. And 10, 15 years ago, people were not even sure we'd ever build one. But look at us now. We have them. We have quantum computers. We've proven that they can happen. So now it's just a case of needing to refine them. Another thing that I actually work on is applying quantum materials into what's called neuromorphic computing. We've probably all heard about the AI revolution and how the AI revolution is taking a lot of power, needs a lot of power. One of the reasons it's so power hungry is because we're taking these AI codes, machine learning codes, and we're cramming them into silicon computers that weren't designed for it. Your brain runs those kind of intelligence codes all the time, and you only need to eat some oatmeal in the morning and you're fine for a few hours, right? So if we had the right kind of computer architectures, then AI would take less energy. So I work on a quantum material called vanadium dioxide that has some interesting properties that can help, we think, contribute to creating brain-inspired computers, because this quantum material can do things that mimic synapses, and it can do things that mimic neurons, which, if you could interleave them in the right way, could be used potentially, we think, to create a completely, a third type of computing
Wow. And does that material that you're using potentially for neuromorphic computing lend itself to like a three-dimensional architecture?
Most of the technologies that are being developed on the films, with the idea, kind of taking a cue from silicon, that you would pattern these things and then make a connecting layer, and then pattern some more and make a connecting layer.
As you look ahead to maybe the next decade, do you see any specific areas where quantum technology could help us solve difficult societal problems?
As we get new technologies and as they come online, I'm a big believer that all of these technological advances that humans do, they help raise the standard of living of everybody. And I realize that's kind of a fuzzy answer, but it's extremely important. I do basic science myself. There are other people who are applied scientists and engineers who really bring the technologies to you. I work more on the fundamental idea side of things that I think is so beautiful. But we all have to be working together in order to develop the new technologies. Things that are basic science today become applied technologies in 10 years or 20 years. So those applied technologies, whatever they are, whatever they end up being, raise the standard of living of everybody eventually. It's going to come, for example, I hope, in breakthroughs in power usage, for example. How good will that be, right? We have an energy crisis. We currently don't produce enough energy for the entire world to raise up to the standard of living that we would like everyone around the globe to have. We're also, I think, going to see advances in on the basic sciences side of things. A lot of these open questions, I think some of those are going to get addressed as people have the quantum technologies to really go in and test them and find out what's going on. We can certainly come up with ideas about what's going on, but ultimately science progresses when we test ideas.
Yeah, I think that's an awesome answer. And I think it also kind of speaks to the fact that a lot of the technologies which change the world can be quite understated, especially when they originate from physics, like the transistor. I mean, you'll always hear people talking about how the iPhone changed the world, which it did, but, the transistor completely changed everyone's lives, but we don't talk about it enough.
Think back historically, can we predict what these technologies look like? We can't. We just rely on the incredible creativity of people. If we hand artists new pigments, great things will happen. A good historical example would be the development of Maxwell's equations of electricity and magnetism. So James Clerk Maxwell had just this stroke of genius on the basic science side of things to notice symmetries in the laws that they had for electricity and magnetism. And his work, he added one term. He added one term to the equations that nobody had thought of yet, and that unified everything by symmetry. It unified electricity with magnetism with light. Could he possibly have foreseen the technological revolution that came about? We're depending on that every single day. When you pick up, when you have a cell phone call, right? You're depending on his theories to send the waves back and forth. Your computer moves information around because of it. Richard Feynman actually has a great quote about this and says, look, taken on the large view, that discovery will probably be seen as the greatest discovery in the past 10,000 years. Could he possibly have seen the information age? And yet it all rests on him having done that basic science stroke of genius to insert that new term into the equations no one had thought of before.
Professor Carlson, I now want to ask you about a Princeton study which was done with a ultra-thin material which was 3 atoms thick. And I read that what the scientists saw was that the effects with regard to superconducting were counterintuitive to what we know about kind of the 2 superconducting materials which already exist. Does any of your work relate to this?
One of the things you bring up there is this ultra-thin material, right? People are always developing new ones and playing new tricks with them. We used to think about the frontiers of science as being like a frontier that's out there and you go and you find it. But we're at a new stage where we are creating the frontier as we go because we can design new materials. Here's a cool trick that people play sometimes is they'll take these 1 atom thick materials and then they'll twist them relative to each other. Well, what happens if I twist one thing relative to another, right? I get interesting new things happening at every angle. So that's a fantastic playground that people are playing with these twisted bilayer materials where interesting effects happen just because of how the 2 materials are laid next to each other.
Being able to have so many different combinations of things that you can do is just probably critical to discovery, because the probability of probably finding something revelationary in there by doing, putting atoms in a certain way, putting them at certain angles, injecting certain amounts of current, certain temperatures. And everyone being able to do that at scale should really accelerate, discovery.
One of the things that's fascinating and exciting to me about the field of quantum materials is that there are so many materials and so many experiments being done on them. We're what's called a data-rich field. There's plenty of room for theorists like myself to come in and try to make sense of it all, as opposed to some fields like particle physics. They don't have many experiments running because the experiments are so large and so expensive. They're very important, but there's not many experiments. On the other hand, in my field, there are experiments coming so fast. It's like trying to drink out of a water hose to understand it all. And that means, so for the young people who are wondering, is this a good field to go into? Which field, has a lot of possibilities? Quantum materials and quantum technologies are wide open. We have a bright future. There's lots and lots of room for young people to come in and bring your new ideas.
All right, Dr. Carlson, thank you so much for your time today and for sharing your insights and your knowledge. And we know that 2025 is going to be a very exciting year as the International Year of Quantum Science and Technology. So best of luck to you and all of your research and work.
Thank you, and thanks for having me. Appreciate it.
Such a fascinating interview with Professor Carlson. Two things really stood out to me about her. Obviously, she is such a renowned physicist, and her work is absolutely incredible. But I think she also recognizes the importance of her being an educator herself and needing to, like she mentioned, make her work digestible and understandable to the general population.
Yeah, and I think when you level everyone up, like society levels up, right? Your ability to engage in technologies which can improve your life. Leveling everyone up simultaneously is for the betterment of us all. And I think Professor Carlson, also referring to Feynman, who is renowned for not only being an amazing physicist, but even to this day, out of all the physicists, his name is the one that's in everyone's mouths in that respect, that he was just an incredible communicator and made physics interesting and accessible for everyone. Because I think another thing about physics is that it does tie really strongly with philosophy, as in it asks the bigger questions about, our world and how we perceive it and what it actually is. So I think Professor Carlson has been incredible in being able to do that in quite a concise way.
Right. And when you think about the way she put it, when you're talking about for the everyday citizen, for the most part, they think that quantum technology is something that does not affect them. It's, above most people's heads. But then when she brings it into a real micro level of when we've got these energy leaks, when you're talking about power lines, now you have the attention of the general public and they're thinking, oh, okay, maybe this quantum technology is a little bit more impactful into my everyday life than I thought.
We live in an ecosystem, Orchia, where everyone plays their part, right? And so, again, how Professor Carlson said about her being the supplier of the pigment for the artists, which are the inventors, right? So curiosity-driven research and that fundamental basic research that Dr. Carlson does feeds into a bigger ecosystem, which has a knock-on effect to benefit, like, the average person. So those inventors take what she does and creates it into something that is usable and can be leveraged by society, and it's kind of a chain reaction. And I think nothing happens in isolation. It's never historically happened in isolation. We're all stakeholders in the world and in society effectively, and physics is the ultimate kind of discipline that attempts to understand our world.
Well, a really great interview, and our thanks to Professor Carlson for her time today. But we still have much more coming up. Layla, what's on tap?
So coming up, we're looking at deepfakes and cybersecurity with Dr. Sway Liu from the University of Buffalo's Forensics Lab and Damon McCoy, who is the co-director of NYU's Center for Cybersecurity.
That is going to be a fascinating interview. Straight ahead. But that's it for today's show. If you enjoyed our discussion, don't forget to like and subscribe because that does help us improve the show. Thank you so much for your time today, and goodbye. Agents of Tech is brought to you by Webb's Edge. Thanks to our studio engineers, our editor, Abby Harries, graphics designer, Matthew Coleman, and our producer, Kath Sheehan.